My name is Fiona King and number is NO47734 and my presentation is on the Guggenheim Museum in Bilbao, Spain. This is an overview of the content that I'm going to run through throughout the course of the presentation. So I'll go through things like the project objectives and the brief, the actual construction and materials used throughout the project, and also impact analysis, risk analysis, and environmental considerations. So as an introduction to the Guggenheim Museum, it was designed by the American architect Frank Gehry. It is located in Bilbao in Spain and works were completed in 1997. Iden were appointed as the sole construction manager for the project. So to go through construction management quickly, it's the procurement route for the client having contracts with the individual subcontractors, where a construction manager is basically in charge of running the everyday project needs. So this is just a list of the contractors that were chosen as the most suitable choice in their field for each aspect of the demolition and construction. So for example, Petrolanda did the demolition of the existing industrial structures as it was formerly a port. You can also see that Ferrovial played a major part throughout the whole project, being involved with the interiors installation, the actual structure of the building, and also the urban infrastructure, which played a big role as it connected the Guggenheim Museum to the rest of the city. So for the project brief and the objectives provided for by the client, I'll firstly run through quickly. So the Solomon R. Guggenheim Foundation was created to promote an understanding of modern art by providing education, exhibitions and publications. So what the client wanted to do with the Guggenheim Museum is to provide a place for this to occur. So it housed contemporary modern art whilst also providing a landmark within the building itself. The museum has been known to create the Bilbao effect. So before the Guggenheim Museum was built, the city was in financial decline, and through the Guggenheim Museum, it's rejuvenated the economy and culture in the city. And as mentioned before, it provides a meeting place surrounded by stimulus for people to meet and to get into contemporary art and be educated on this. So a large part of a project brief and the objectives is the budget, so how much the client wants to pay. This project was government funded as the aim was for it to contribute to the city. The original estimate that was provided was too high, so there was a meeting and the estimate and the requirements for this were revised. So the budget was 127.5 million US dollars, and this couldn't be further decreased as it would have meant that the client wouldn't have achieved their goals. So as a description of the building itself, as mentioned before, it is a museum for contemporary art, and the appearance of the building is different depending on where you're looking at it from. So if you're looking at it from the ground, it most likely looks like this image at the top as a boat. And if you're looking at it from an aerial view, it looks like a flower. Frank Gehry explained that this was done so it blends in with the landscape, so the boat blends in with the river that it's right next to, and the flower adds to the environmental landscape. The location of the Guggenheim Museum is easily accessible from the city, as the main street that goes through Bilbao leads straight onto the museum at the end. The building was designed so that it stands neatly between the river and the city, so that the building doesn't rise above the neighbouring buildings, so it doesn't cause an impact on the landscape. It was built on the former wharf because the banks of the river needed to be recovered from the industrial use so that its purpose is more leisure and culture and to bring tourism into the city to rejuvenate the economy. So to take you through the floor plan of the museum, on the ground floor we've got the auditorium we've got a gallery placed centrally. You've got a store next to that and a fish gallery. And the atrium here is the main entrance of the building, a big glass front, so you can't miss it. Tickets are sold over here, and again we have another store with facilities towards the rear and ponds next to the fish. On the first floor, we've got the library, a restaurant next to that, the galleries here, and again the atrium extends to the next floor. And for the second floor, these areas are just roof. You've got the stairs at the side, which are encased in glass. Again, the atrium extends to the top of the building to make an impressive entrance, and more galleries. And here are just voids, so the first floor looks up and has a wide open space. A few key features of the buildings are that the stairs and the lifts are encased in numerous glass panels that were made to look like fish scales. Obviously there's the initial impact you get of the building, which has a titanium skin, which reflects differently in the light, which we'll be running through later, and also the open atrium and balconies that surround the atrium area. So initially, for the materials and the construction of the Guggenheim Museum, I'm going to talk through the titanium outer skin. So experiments were conducted to get the correct mixture of chemicals and heat when titanium was rolled. So bitumen was thought to be used initially to waterproof the building because of its viscoelasticity and its ability to adapt depending on the environment. However, this had the issue of becoming brittle once set. So after the experiments were done, it was found that bitumen with an added rubber layer would mean that this would waterproof the Guggenheim. This mix enabled the titanium plates to be screwed onto the steel frame, and with the bitumen material healing itself around the screws by reforming, and this is what made it watertight. So this is a comparison of the properties between steel and aluminium. The tensile strength is dependent on the grade of titanium steel, hence why there's a difference in the numbers there. So the question is, if titanium is better than steel, why not use it everywhere? Titanium usually is vastly more expensive than steel, and it was only due to a sudden drop in the price at the time of construction that Gehry was able to use this material to achieve his desired look for the building. Titanium reacts with oxygen to form a layer of titanium oxide so that it doesn't corrode, as demonstrated in the table. This meant that it could be protected from the polluted air, being a former port city. The effect that this also had was that it gave it a golden finish to the colour. The science behind this is that titanium reflects light differently, depending on where you're standing from it and how you're looking at it. So some light reflects off the oxide layer from the titanium, whereas some reflects from the actual titanium itself. When the two different reflections meet, they partly cancel each other out, and this is when some light is removed from the white light. This is when we get coloured light. So the Guggenheim Museum, the titanium sheets have the thinnest layer of oxide, which makes the titanium appear a light gold colour. So if the titanium was to be further oxidised, this would change the colour and the entire appearance of the building. So to go through the glass, the atrium and the wall of the atrium as you approach the building is entirely made of glass panels. And this was specially treated to allow the sunlight in, but not the heat during the warm months in the Spanish summer. Another material that was used was limestone, and it was used for both interior and exterior purposes. This was chosen for the building especially because it withstood humidity and rain, which during the wet, colder months and the hot summer months was beneficial for the building. Special clips were designed and manufactured to fit the limestone panels to the structure, and to further support the panels, steel cables were used as an extra support, just in case a panel became loose. So moving on to the interior steel structure of the building, Skidmore, Owings and Merrill were the structural engineers, and they created a modular lattice steel grid system, especially for the Guggenheim Museum. Little scaffolding or support was needed to build the structure due to the steel frame and the curves which supported its own weight. Steel rods were connected by steel nodes, and horizontal bearing plates were used to enable exact directional changes required to create and support the curvature of the structure. Further on from that, high strength bolts were used to connect the elements together. So this next slide is going to talk about the science behind the curves. So I just wanted to pick up on the point of how curvy you could say the building is. And to do that, I'm going to use an example of an egg. So if you look at the shape of an egg, there's a double curve. So you see the curve both sides. It's a symmetrical shape and is longer vertically, and there is quite a dramatic curve in the egg. So from physics, this basically means that an egg is strong, and this can be applied to the Guggenheim Museum in the way that it was built. Because it's curvy, it supports its own structure very well, and the engineers actually requested for the building to have more curves and have more dramatic curves, as it created a better support for the building itself. So here are just a few figures for you to look through, just demonstrating how large the project was, with the amount of foundations that we used, the amount of concrete and cabling used in order to keep the building going. So to go through the substructure systems used of the Guggenheim, due to the situation of it beside the Nervion River, it would have been likely that the soils didn't have the sufficient bearing capacity for standard foundations such as the slab, as it is such a large structure and made of a steel frame. So because of these soil types, the displacement piles were used for the Guggenheim. This meant that the soils would have been pushed downwards and outwards, having the effect of compacting the soils in the ground. Generally, this can be done through being driven, screwed, or vibrated. So in this instance, the piles were driven into the ground, and a special system that were used were water anchors, and this was needed during the construction of the Guggenheim, just in case the river would flood. How this was done was that the piles were driven into the ground and their centres were bored out. A cable was then fed through this centre into the bedrock, with the piles then being filled back in with concrete. The cables were then tied tightly at the top to counteract any buoyancy that may occur should there be a flood of the river. Pile caps were then used instead of pad footings, as they're usually deeper and evenly distribute the load to all of the piles that they serve, providing a better stability and base for the Guggenheim Museum. The depth of the pile cap would have been determined by the ground shrinkage and swelling, the water table, and also pile anchorage. In this instance, the piles were around a depth of 14 metres into the ground. Another foundation system that was also used was micropiling as well as the driven piles. Micropiling can be used in most ground conditions, and it's especially useful in areas where access is difficult. Micropiling in the case of the Guggenheim was for additional support to the building structure, and this was used in combination with the 14-metre long reinforced piles. Micropiling is good as piling rigs can be low in emission, or they can also be electronic, therefore they're also better for the environment. Micropiles also have high load capacity and are good for resisting tensile, lateral and compressive loads. This is important related to the Guggenheim Museum, as despite not rising above the city, it's still 57 metres in height and clad in a light titanium, therefore it is subject to wind load. So this is a quick visual of how the Guggenheim's exterior was put together. So first off, there is the core of the steel frame. Outside of this was galvanised steel tubes, which were 60mm diameter to create the curves of the outer skin. There was a universal joint that was used to connect these tubes to the steel frame so that fine adjustments could be made according to the curvature of the building. After this, there was thermal insulation and galvanised steel cladding, and then there was a bitumen membrane, which, as I've been through before, was the bitumen with the added rubber for waterproofing the building, and finally the titanium tiles, which were screwed to the layers on top and crimped. So to continue with the management of the materials used in applications, so a steel frame can be melted, so what would happen in the event of a fire? The solution to this, it was decided that mineral wool would be used, which is made from volcanic rock. So this volcanic rock is made by when a volcano erupts, lava is spun into glass fibre, and this became the insulator, which is the mineral wool. How it works is that small pockets of air within the material prevents the heat from transferring quickly, and this was sprayed onto the Guggenheim steel structure. The effect that this has is that it protects the structure for up to 4 hours from a fire. So for flooring and roofing systems, gun placed concrete, also known as gun concrete and gunite, was sprayed into a plywood formwork to form the walls and ceilings of the building. The concrete had to be sanded down to a sand finish surface to complete the look of the building, and terrazzo flooring was used throughout the Guggenheim. This terrazzo flooring is basically small bits of marble or granite in concrete which is smoothed down. This was used as its hardwaring, and there's continual maintenance on this, with careful and consistent repairs being conducted to maintain the quality of the floor. So for maintenance services and external works of the Guggenheim Museum, a custom project is made for each incident where maintenance works are needed to be carried out. There's also a conservation department where there is a temperature which is set, and also humidity for the artwork, and also airflow must meet the conditions required. Obviously from the outside, the titanium and the glass need cleaning, and the cleaners abseil from anchor points in order to clean the exterior, and this is done on a daily basis. Flaws have also been solved by creating new systems, and with technology changes over the years, old systems have been replaced with the new, and this has been more efficient for the maintenance of the Guggenheim. This is a picture of Frank Gehry's initial sketch of how we envisioned the building. So moving on to systems, I'm going to go through how this sketch turned into a functional. So CATIA played a major part, being the main system involved in this project. CATIA stands for Computer Aided Three-Dimensional Interactive Application, and this was a 3D design piece of software. It was developed initially by Dassault Systèmes, which is a French company, and prior to the Guggenheim being built was used for aircraft, for example by Boeing and the US Navy. And this piece of software is useful for innovative designs and shapes, and there are many different arms to it, for example M&E engineering, design and fluid systems, so for example piping and heating. So this system enabled where and how the steel bars were fitted and how many were needed, which is essential for the number that were used and the exact location that was needed. So experiments were essential to create a robust external face. to achieve the desired aesthetic, and this is where Katia came in and did all of the hard legwork for them. Homer Eaton in the 1970s created the articulated measuring arm, which also played a massive role in the building of the Guggenheim. This articulated measuring arm worked by placing a sensor on the item to be measured, which produces an X, Y, and Z coordinate, therefore providing the 3D information to be used on Katia. So the way that the titanium skin was put together for the building, there's a quote here from Luis Rodriguez Lopez, and he said that we found that it was easier to hire climbers and train them as crimpers than to hire crimpers and train them as climbers. The building was too complex to use standard means of constructing the titanium outer face. Therefore, they trained climbers to crimp the titanium rather than the other way around. So different atmospheric pressure was also used as another system. So the atmospheric pressure inside the museum is higher than that which is outside. So outside, the atmospheric pressure rests at 1 atmosphere. Inside, the pressure is greater, so that when the doors open, the air tries to get out rather than creating a draft within the museum, which is all about the aesthetics and how people feel within the museum. This is opposite for the laboratories. So the pressure is lower inside, so that when the doors open, any laboratory smells are kept inside rather than escaping to the rest of the museum where the artwork is located and where people are viewing the artwork continuously. So going through risk analysis, from the Guggenheim Museum, I've come up with these points that would be brought up, say if a risk register would have been done. Obviously this list isn't extensive, but just as a few points, using materials like concrete, cladding the entire building in titanium and combining bitumen with added rubber weren't common methods used previously in construction. Therefore, there was a risk in that there can be no definitive evidence of how the materials may react in years to come, or that the finish once completed wasn't what was envisioned by the architect. This would mean a cost or time overrun to change the materials or the methods that were used. Also, with such a high volume of people working on the project, and also with there being a global project team, would mean that there was a higher risk for the team not to integrate properly, and therefore cause potential issues such as overrunning on time, cost and quality. Also, for such a large project, it was essential that time and cost, which are related, were not exceeded upon, and a small mistake could mean a lot of time and money, which you could argue is the same on most construction projects. So doing an impact analysis of the construction of the Guggenheim Museum, obviously the pros outweighed the cons during the time of the construction. However, some examples of pros would be that it rejuvenated the economy and was an example of innovative construction within industry. Also, the cons to look at would be the actual buildability of the project, if this was achievable, and also the potential, because of it being such a large project, of cost and time overruns, and also the maintenance of it, as it's a lot of building and the purpose of it is a lot to maintain. So the maintenance costs may outweigh the build costs. So innovation management. So on a daily basis, workers from Ferrovial inspect the interior and exterior of the building to ensure that there is no damage. If there is, a project is raised for each maintenance issue produced. And this is followed through to ensure that it has been rectified, and this is the way that this is managed. Going back to throughout the construction of the Guggenheim, regular meetings were held alongside using Katia to ensure that the designs were on track for what the client required, also meaning a close eye was kept on the budget if there were any design changes. This also meant that the project team would be more integrated as they met more regularly. So finally, to come on to the ecological and environmental considerations. So first of all, there is the shape and resemblance of the building to blend in with the landscape of the river and to not be a massive eyesore for Bilbao as it blends in with its surroundings. Environmentally, there is a neutron lighting system. So this is an integrated lighting system which has energy saving modes. So for example, occupancy, vacancy sensors. You can also use away modes, and this can all be done from a wall control panel or handheld device. There's also the point to bring up that most of the halogen lights have been changed to LED, and the museum is working towards having all of the LED lights, which is saving them a lot of money yearly. Filtered light wells were also used in the ceiling so that the light can be controlled when viewing the art. This meant that the art is protected from the strong sun in summer, and the filters can be adapted in the winter to let more light in so they can be removed. The use of high ceilings and the filtered light wells in the ceiling and upper galleries also meant that less energy would have to be used through the light bulbs as natural light would be entering the building. And that is the end of my presentation. Thank you.